Hello, everyone. In this video, I'm going to talk about how to implement binary tree in C programming language. Also, I will talk about binary search tree, which is a special type of binary trees. And it implements set abstract data type. And then I'll talk about the insert operation, search operation in a binary search tree as well. Then I'll talk about how to do pre-order traversal, post-order traversal, and in-order traversal in any binary tree, including in a binary search tree using recursion. Then I'll show you how to calculate the height of a binary search tree in a recursive fashion using a C function. Also, we'll see a C implementation of a recursive count operation that counts the number of elements in a binary search tree. Also, finding the min and max value using recursion in a binary search tree will be shown in this video. And finally, I will show you how to do a breadth first search traversal of a tree, of a binary tree, and also a binary search tree using a queue abstract data type. A queue is a first in first out data structure. In order to do that, I show you the implementation of a queue using a linked list. Queue can be implemented in different ways. What we see in this video is implementation of queue using a linked list. For the insert operation or the in queue operation, I will append an element to the end of a linked list. For the dequeue operation, I will remove an element from the beginning of a linked list. And that's how I can implement queue using a linked list. So let's get started. A binary tree, by definition, is a tree in which every node has at most 2 children. What is a tree? You can say tree is a connected acyclic graph. Or in a different way, you can say tree is a data structure that has a root, and each node has a left child and a right child. The left child would be the root of the left subtree. The right child is the root of the right subtree. So basically, the root has a left subtree and a right subtree, and the left subtree is a binary tree as well. So you can define binary tree in a recursive fashion. But the mathematical way is to say that a tree is basically a connected acyclic graph. Let's see how to implement a binary tree using C structures. This is a C struct. It's called T node, and T stands for tree. So it's a tree node basically. It stores values of type integer in it. We can, generalize this structure definition by replacing the type of value, by making type of value equal to void star. So replacing int with void star, that's possible, but I don't want to do that because later I want to show you binary search tree. So the value must be comparable, and int is a common comparable data type. So I'm going to leave it as int for the sake of simplicity. Also, what else do we need for the T node? We need a left subtree reference. So we need to have a struct T node star left and a struct T node star right. In that sense, you can think of binary tree as an extension of a linked list, as an extension of a single linked list. If you remember, in a single linked list, every node has a reference to another node. That reference is called next. Here, for a binary tree, every node has two references to two other nodes. One is left, one is right. So you can think of a binary tree as a 2D linked list. Okay, so that's basically my structure that allows me to store a single node of a binary search tree when you have, I'm sorry, a binary tree, when you have many instances of this structure, which are connected together, you can create a binary tree with, different number of nodes. I'll show you how to do it. Then I have a type def to give a shorter name to my T node. So instead of saying a struct T node, from now on, I will call it T node. That's what this type def does. All right. After this brief introduction to binary trees, I'm going to define binary search tree. A binary search tree is basically a binary tree with a special property. The property is this: the value that is stored in the root is greater than all the values that are in the left subtree, and it is smaller than all the values in the right subtree. And this property is true for every subtree in the whole tree. That means, for example, the root of the left subtree is greater than the left subtree of the left child of the root, and it's less than the right subtree of the left child of the root. So that means you have this property recursively true in the whole tree. And I'm not going to explain it too much because I'm going to assume the viewers know already what binary search tree is. This is just for review. And also, binary search trees are very popular because they are a decent implementation for set abstract data type. That means what? That means you can use a binary search tree to store a set of elements. When I say set, that means we're going to have a collection of elements where duplicates are not allowed, and the order of insertion should not be preserved. Otherwise, we would use a list, not a set. So set is a different data type compared to list. In sets, despite lists, we are not allowed to store duplicate values. And also in sets, we don't need to preserve the order of elements that are inserted. So you can store them in any order you want. Later, you will see that, other than binary search trees, you can use hash tables to implement a set abstract data type. But, today's topic is binary search trees. With that introduction, we're going to talk about how to insert or search in a binary search tree. The reason we call this data structure binary search tree is because the search operation is pretty fast. If the binary search tree is balanced or semi-balanced, the complexity of search operation is order of log n, and log n is pretty fast compared to linear search where the order is n. Log n is pretty fast. And then the insert operation would be order of log n, assuming that the binary search tree is balanced or semi-balanced. So the next thing I'm going to show you is this implementation of insert and search operation in a binary search tree. My assumption is there is a root for the binary search tree stored in the caller of this function. So let's start at the insert operation. Let's say we already have defined a root in the color of insert. Later, you will see that, we have a root. Let me briefly show it to you here. In the main, I have created a root pointer, which is a, t-node star. And I'm going to assume that this root exists, right? So let's say we have a t-node star root, right? The insert will receive the root by pointer or by reference. So that means we have to pass the reference of a t-node star to insert. That's a t-node star. And we're going to pass the value that we're going to insert to the binary search tree. So what does insert need? The pointer to the root and also a value. The value that we want to insert. It also returns some value. It returns an integer. Why do we return an integer? That integer basically specifies whether the insert operation is successful or not. If it's successful, it returns 1. If it's not successful, it returns 0. You may say, why an insert operation? Why can an insert operation fail? An insert operation can fail in a binary search tree if you're inserting a duplicate value, right? So it's not like inserting to a list that always succeed. It may succeed or it may fail. So let's see how things look like. I'm going to do the insert operation in a recursive fashion. I'm going to start this way. I'm going to say if my root, which is, asterisk applied on root P because root is passed by reference. Whenever I'm going to access root, I have to say asterisk applied on root P. If asterisk root P is null, that means if my tree is empty, then do this. Let the root P equal to some space in the heap. How much space do I need to allocate? I need only one node because the root is only one T node. So I will allocate enough space for storing a T node. Then I will set its value equal to the value that I'm going to insert. I will set the left and right child equal to null because that's the very first node that I'm going to add to my tree. And then I return 1. 1 means it's a successful tree. It's a successful insert operation. Now, this is the base case of my recursion. Because tree is defined recursively, all the operations that we're going to show here, with the exception of BFS, which is breadth first search, will be implemented recursively. BFS is an exception because we're going to use a queue instead of recursion to implement it. All right, so that's the base case. If the base case is not true, that means if the tree is not empty, then what do? We are going to retrieve the data stored in the root, which is this amount. If it's equal to the value you want to insert, you can return 0, which means the value is already in the root, so that's a duplicate value. You don't need to insert. No insert is needed. And that's it. That's kind of the second base case. However, if the value is not equal to the value stored in the root, let's say the value is greater. So you need to insert the value in the right subtree of the tree. So how do you get right subtree? Basically, you need to apply the asterisk on root P because root is passed by reference. Then arrow right is going to give you the root of the right subtree. And then you need to pass the root by reference. So you apply another ampersand on it. And that's going to basically insert in the right subtree, inserts the value in the right subtree. Why did we insert in the right subtree? Because the value was greater than root, and the binary search tree definition says all elements greater than root should be stored in the right-hand side. So this is written this way because the way we define binary search tree. If it's neither equal nor greater, then we're going to reach to the very last line, and then we're going to return this. We're going to insert the value in the left subtree. So basically, it's a symmetric case compared to the line 31. So instead of inserting it in the right-hand side, we insert in the left-hand side subtree because the value was smaller than the root value. And that's the insert operation. I have used this insert in a function called make BST, and in the make BST, I have called the insert repetitively in a for loop just for the sake of simplicity. Let's say you want to create a binary search tree given an array of integers, and the size also is given for that array. And then make BST will create a binary search tree and returns the root of that tree as the return value. How do we do that? Basically, you create a parameter, create a variable of type tnode star, call it head, set it equal to null. Null means originally you have an empty tree, and then in a for loop, call insert, pass head by reference, and basically insert the ith element of the array. Do this for size, number of iterations. After you insert them all, then you can return head. Head will be returned, and make BST basically can construct a binary search tree with the values inserted in this array. So just to test my insert operation, I have done something in the main. In the main, I have created an array of elements. As you see, for the sake of testing, I have made duplicate value as well to see if this binary search tree is going to remove all the duplicates, as it should remove the duplicates because it's a implementation for a set, not a list. And also, does it insert all the elements in the right order or not? So I have called the make BST on the array, and then the length of the array is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I pass the array and its length to the make BST, and that's going to construct a binary search tree if the insert operation is correct, and it's going to return the root. I'm not going to run it till the next 10 or 20 minutes, because I'm going to first explain the traversals and the search operation. Later I'll run it and you'll see that all of them work as expected. But just to show you what you expect from this line, I should say that by calling this, root will be the root of a binary search tree with 8 elements. Why 8 elements? Because out of these 11 elements, these 3 are duplicates. So 11 minus 3 is 8. So we will have like 8 elements in our binary search tree. Next, I'm going to talk about the search operation. The search operation in a binary search tree is very simple. It's much simpler than the insert because you don't want to add anything, just want to look for a value. Let's say you want to search for this value in a binary search tree whose root is given, right? How do you do this? Let's take care of the base case first. In the base case, you basically check whether tree is empty or not. If tree is empty, then you need to return 0 because empty tree has no value in it. Therefore, the value that you're looking for is obviously not there. So we return 0. 0 means an unsuccessful search. If that doesn't happen, then what do? You compare the value with the root value. If they're equal, then done. You have a successful search, you return 1. Otherwise, it's either greater or less. If it's greater than the root value, then you need to call the search recursively for the right subtree, because if it's greater than root, it can only be found in the right subtree because of the definition of the binary search tree. If it's neither equal nor greater, so it must be less. So let's continue the search in the left subtree and pass the same value and see if you can find it in the left subtree. So that's basically the search. I have tested the search inside main. Let me show you the test. I have said, let's find out, for example, to see if, let's find out whether or not 2 is in the tree. So I have said %d is %s in the tree. The %d is replaced by 2, and this %s is either replaced by an empty string or a not word. So it depends on the result of the search. If the search returns true, returns 1, that means the %s will be replaced by an empty string. So when you read the sentence, it says 2 is in the tree. If the search returns 0, that means it's an unsuccessful search. Then it says 2 is not in the tree. Of course, 2 is in the tree because 2 was part of this array. So this should print 2 is in the tree. I have repeated the same test for 9. Because 9 is not in the original array, it should not be in the tree. So what you should see for this line is 9 is not in the tree. We'll run it later and see the result. The next thing I wanted to mention in this video is pre-order, post-order, and in-order traversal. Before doing that, let me draw the binary search tree that will be resulted in line 150. If everything works properly, which I'm pretty sure it's going to happen, then what we will have is something like this. We will have a root with value 4 in it. We will have, because of the first value is 4, we will have 6 in the left-hand side, I'm sorry, the right-hand side, because 6 is greater than 4. Then we're going to see the next one is 1. Then we will see 1 here. Then we will see 0 in the left side of 1. Then we will see 3 in the right side of 1. Then we will see 5 in the left side of 6. Then we will see 7 in the right side of 6. And then we will see 2 in the left side of 2. I'm sorry, left side of 3. So these are the 8 values. Of course, the insert operation for 1, 0, and 3 will fail because we already have them in the tree. So consider this tree, right? There are different, I should say, there are different traversals for the tree. What does traversal mean? Traversal is a special ordering of elements in a tree. So, or basically iterating through the elements in the tree in a special way. We have different traversals. We have a pre-order traversals when you first traverse the root, then you traverse the left subtree, then you traverse the right subtree. So, if I want to do the pre-order traversal, I should start from root, so it's going to be 4. Then it's going to be the left subtree. Then after 4, I have the left subtree, and the left subtree starts from its root. So after 4, I will have 1, and then after 1, I should traverse 0. After 0, I should traverse the right subtree of 1, which is going to be basically 3 and 2. After the whole left subtree is traversed, then we're going to traverse the right subtree in the same order, pre-order traversal. First 6, then 5, then 7. So if I want to quickly write that down, the pre-order traversal would be 4, 1, 0, 3, 2, 6, 5, and 7. That's the pre-order traversal. Now let's talk about post-order traversal. Post-order traversal basically traverses the left subtree, then the right subtree, and then finally the root. So for the left subtree, we're gonna do the same thing. First this node, then these two nodes, then the root. For the right subtree, first we do the 5, then 7, then 6. That's called post-order traversal. Let's write this down as well. The post-order traversal would be, would post here. As I said, left, then right, then root. So it's gonna be 0, then we're gonna have 2, then we're gonna have 3, then we're gonna have 1, then 5, then 7, then 6, and then 4 is the very last one, right? Sorry. All right. So that's gonna be the post-order traversal. And finally, we have one more. It's called in-order traversal, which traverses the root at the middle. First the left subtree, then the root, then the right subtree. So if I want to do it for this tree, the in-order traversal would be 0, then 1, because in the left first you need to do the left subtree. In the left subtree, the leftmost child is 0. First 0, then the root, which is 1, then the right subtree. Right subtree should be traversed in order. So first 2, then 3. And after that, we gotta have 4, which is the main root, then the right subtree. The right subtree, first we traverse the left child, then the root, which is 6, then the right child, which is 7. So if you look at this, you see that the numbers are sorted increasingly, and that's not an accident. That always happens when you have a binary search tree. That's the property of binary search tree. The in-order traversal would be increasingly ordered. And that's pretty much the beauty of binary search tree. The traversal, in-order traversal is basically an increasing ordering of the elements stored in the set, in the binary search tree set. All right, so with that said, now that you know what pre-order, post-order, in-order is, let's get into the implementation in our example. So far we have seen how to create a binary search tree, how to insert, how to search for an element. Now let's talk about the tree traversals. Let's do the pre-order first. The pre-order traversal, basically, it's a pre-order print because whenever I'm gonna visit a node, I'm gonna print it. So I'm gonna first take care of the base case. Whenever you wanna do whenever you wanna do a recursive operation, take care of the base case first. What is the base case? The base case is when the tree is empty. When is the tree empty? When the root is null. So if root is null, I'm not gonna print anything. So this if is taking care of the base case, basically, because if root is null, then you never get into this if, and you're just gonna skip the whole thing and you just want to return immediately. So that's the base case. In the recursive step, which is inside this if, this is what we're gonna do. We're gonna first, in the pre-order, remember the root is traversed first. So we're gonna first visit the root by printing it. Then we're gonna call the same function recursively for the left and then for the right subtree. That's it. This recursive operations the recursive implementation of different algorithms look very simple and straightforward when you know what the recursive formula is or what the recursive step is. The base case is always simple, but the recursive step is a little bit tricky after you realize what the recursive step is. Implementation is always short and simple and straightforward, just like this. After pre-order traversal, let's talk about the other one, post-order traversal. You have the root as an input parameter. All you need to do is first make sure it's not null. If it's null, don't do anything. If it's not null, then first traverse the left subtree, then the right subtree, and visit the root by printing its value at the very end. Then we have the in-order traversal. In-order traversal basically is the most common way of traversing a binary search tree, because it's going to print the elements in order. The first thing is taking care of the base case. If root is null, don't do anything. Then we're going to do the left subtree traversal first. Then we're going to print the root. Then we're going to call the same function recursively for the right subtree. So by reordering these 3 lines, we create 3 different traversals. And that's the beauty of recursion. It's very simple, very straightforward. All you need to do is take care of the base case, take care of the recursive step. Later, I'll run this. And when I run it, you will see that the in-order traversal will be the same as what I wrote here. The post-order traversal will be the same traversal that I write here. And the pre-order traversal would be this, the one that I wrote here, the one that starts with 4. So we'll run this and you will see that everything is working the way we expect. Now, the next topic I want to talk about is height. How to calculate height and count of a binary search tree in a recursive fashion. That's my step 5. Let's take a look at the height function. Again, the base case is when the tree is empty. When tree is empty, I assumed I return -1. -1 is basically by definition the height of an empty tree. Just for those of you who are wondering why -1, I can say this. I can say height of a tree with only 1 root node is 0. Why? Because height is defined as the depth of deepest leaf, or another way you can define it this way. You can say is the distance of where the distance of the furthest leaf from the roots. So the one that is the most far from the root, the leaf that is most that is furthest from the root, has a distance. That distance, which is the length of path between that leaf and the roots, is considered to be the height, right? So because of this, we define the height of an empty tree equal to be -1, because if you want to use the definition, the height of furthest leaf from a root, the root doesn't exist. So the distance doesn't exist. So the height cannot be even defined. But because we are doing this recursively, we try to set this to a value that makes sense. Let me first explain the recursive step. In the recursive step, we say you want to measure or calculate the height of the whole tree. First, calculate the height of the left subtree, then calculate the height of the right subtree, get the maximum of those, the longest one, and then the height of the longest subtree would be 1 less than the height of the actual tree. Why do we have a 1 plus? Because the height of the actual tree is 1 more than the height of the longest subtree. That kind of makes sense because the actual tree has an extra root on the top, so it has 1 more level, so it must have a higher height, or it must have a greater height, I should say. So the recursive step is this: 1 plus the maximum of the height of the left and right subtree. Because of this recursive definition, assume that you only have one node, right? If you have one node and that's it, the root is also a leaf and there's no other node, the root has no children. In that case, the height of the children would be height of 2 empty tree, right? The height of 2 empty tree plus the maximum height of 2 empty tree is basically the same as maximum. It's basically the same as the height of an empty tree. Height of an empty tree plus 1 should give you the height of a tree with only one node. Because we have defined the height of an empty tree, the height of a tree with only one node to be equal to 0. Therefore, 1 plus the height of an empty tree should be 0. What should be the height of an empty tree? If you solve an equation of 1 plus x equals 0, you will get x to be -1. That's why I put -1 here. So I put -1 because the recursive formula demanded -1. So I set it equal to -1. Otherwise, you don't even define the height for an empty tree. All right. So if the tree is empty, we return -1. Otherwise, we use this recursive formula and everything would be working perfectly because of recursion. The count is much simpler. And you want to find the count of an element. If you want to count how many elements you have in a binary search tree or generically in a binary tree, you first check the root. If the root is null, the tree is empty, so you return 0. Otherwise, you're going to return 1 plus the number of elements in the left subtree plus the number of elements in the right subtree. What is the extra 1 here? That's basically the count of the root, right? So that's basically the implementation of count. And then the next step is the mean and max values. Based on the definition of a binary search tree, the mean value is the leftmost value and the max value is the rightmost value. So we're going to do this recursively to find the leftmost child and the rightmost child in a binary search tree. The mean value is defined this way. We have 2 base cases. If the tree is empty, so the minimum doesn't exist, to do that, to return some value, we return them the minimum integer value. That would be this number. You don't need to return anything. I return the minimum possible value just to show that something went wrong. And that's the exceptional case. If in the next base case, I have if root has no left child. If root arrow left is null, that means if root has no left child, I'm going to return the value in the root because root would be the leftmost element. And otherwise, I'm going to call the same function recursively, and I'm going to pass the root left to it. So this way, I will eventually find the leftmost node. For the max value, similar stuff. I get the roots. If it's null, that means I have an empty tree. I will return the maximum possible integer, which is 2 to the power of 31 minus 1. If not, then I check whether I have a right child. If there's a right child. If there's a right child, for the if there is no right child for the root, I will return root value. Otherwise, I will call the max value recursively for the right child. And that's how you take care of the max value operation for a binary search tree. Finally, I'm going to introduce an implementation for Q, which is a first in, first out data structure. And I'm going to use a linked list. To do that, the queue you already know. Let me draw that briefly. A queue is basically a data structure that has two ends, despite what we had in stacks, which only has one end. A queue has two ends. One is the head end, the end that you dequeue, and one is the tail end. That's the end that you enqueue. So you enqueue from one end, dequeue from the other end, and that will give you a first in, first out data structure. How do you implement this? You can use arrays, but it would be very inefficient unless you use a circular array. But the easiest way to implement a queue is to use a linked list, and that's exactly what I want to do. So I'm just gonna make my queue as generic as possible. That means I'll try to make it in a way that you can store anything in your queue. It's a very simple implementation. Let me explain how it works. I first create the node structure for my linked list, because queue is going to be implemented using a linked list. And because the value should be as generic as possible, I define it as void star, and there's a struct node star next that always refers to the next node. And I will type def my struct node to node. And then after that, I will define my queue in this way. I will say, let's define another structure. It has a node star head, and it has a size. I start the size as well, so that I never have to count how many elements I have in my queue. If the queue is empty, size will be 0. If it's not empty, size is greater than 0. If I want to see how many elements I have, I read the size, and I call it a queue. So queue would be basically the structure made of a linked list head and a size integer. Then I will define an enqueue and dequeue operation. Enqueue is for adding an element. Dequeue is for removing an element. This is what I'm going to do. My enqueue would be append to the end, and my dequeue would be remove from beginning, right? So remember this for till the end of the lecture. So I'm going to start with enqueue operation. Let's say you have a queue pointer. I'm going to pass it by reference because I'm going to change the size at the end of this enqueue operation. So I need to pass it by reference. And then I will have a value that I'm going to insert or enqueue to my queue. So that's basically these are the input parameters. What's the return value? I don't need any return value for my enqueue function. How do I manage the enqueue operation? First, let's assume the queue is not empty, because if it's not empty, it's a different operation compared to when it's empty. If it's not empty, that means if the queue's QPR size is not 0, then do this. First, find the head of the linked list that queue stores, which is QP arrowhead. Store it in a temporary pointer, and use this while loop to go to the tail of this linked list. Because remember, in enqueue, I have to append to the end of the list. So I need to go first to the very end of the list. So this is how I do it in a while loop. Then after I reach to the very end, I will do this. I will say, let's set the temp next to a new node, because I'm going to insert a new node. Temp next is null. So that new node would be a new tail. So it has no next. The next should be null. And temp next value should be value. So that tail node will have the value as its value. So it stores the value. That's when the queue is not empty. If it's empty, then it's a little bit simpler. The implementation is different, obviously. I will say the head should be equal to a new location. By calling malloc, I'll create a new location in the heap. And then head value would be value. head next would be null because that's the only node in the linked list for the queue. And then finally, I will say queue size should be incremented because I'm adding an extra element. For the dequeue operation, we do a similar task. I need to pass the queue by reference because I'm going to do size minus minus. So I need to access the queue by reference. Then I will return the value that the queue head will contain. Remember the idea, because the queue has two ends, tail and head. My assumption is head is always the end of the linked list and tail is the beginning of the linked list. So when you dequeue, I'm sorry, the opposite, because you're going to dequeue from the head. I'm going to assume the head is basically the head of the linked list, and tail is going to be the tail of the linked list. So always in queue, but when you're in queuing, you just add to the tail. And when you are dequeuing, you are removing from the head. That head of the linked list is corresponding to the head of the queue, where you have to remove elements from. So we're going to remove the element from the head of the queue, right? So we have to remove the element from the head of the linked list. Where is the head of the linked list? It's in the queue head. So that would be my removed node. I will free this. Before freeing it, let's grab the value that removed that the removed element is going to refer to. Let's avoid the star. Then that's the return value at the end. I should return this as a return value of the dequeue. Then I will set the queue head equal to the remove next, because now the head should point to the second element, because the first element is going to be removed. So we update the queue head. Then we're going to free the removed elements. Size will be decremented, and then we're going to return the return value. So that is the dequeue, and this is the enqueue. Now, why did I start going over queues? Because, you know, this module covers queues and binary search trees, but I have another reason why I'm covering queues and binary search tree in the same lecture. The reason is queues can be used to traverse a binary tree, a binary search tree, and even in a generic fashion, I can say it can traverse as any graph in a breadth first search manner, or a BFS manner. What does BFS mean? So far, we have seen three traversals: pre-order, post-order, and in-order. Now, let me show you the next type of traversal, and that would be called the BFS, or breadth first search. I'm going to traverse the elements level by level. First 4, then 1 and 6, then 0, 3, 5, and 7, and finally 2. In order to traverse the elements in the order I just said, instead of using a recursion, we're going to use a simple queue, and I'll show you the algorithm in the next 5 minutes of this video. Basically, all we need to do for this BFS operation is that after receiving the root from the input, we will do this. We will create an empty queue. The head is null, the size is 0. We're going to pass this queue by reference to an enqueue function, and we will basically enqueue the root of the binary search tree to this queue. So enqueue &q comma root. Let me, while I'm showing you this, I'm gonna show you how it looks like in the example that we have on the screen. So first, I'm gonna insert 4, right? So 4 is inserted here. This is the tail, this is the head. So 4 goes to the head of the queue, right? Then in a while loop, as long as the queue is not empty, queue.size means queue size is not 0. That means Q is not empty, do the following. Remove the head of the Q, so remove 4, call this current, insert its children, which are from 1 and 6, into the Q. So as you see, it says if the left child exists, in Q the left child. If the right child exists, in Q the right child. In this case, 4 has 2 children, 1 and 6, we insert both of them. So 1 will be inserted here and then 6. And then it's going to print the current value. So we remove 4, we're going to print it. So I'm going to print this here, and I'm going to call this BFS. This is the BFS traversal. So the first thing that will be printed is 4. Just to stay with me, I'll go all the way to the end. Next iteration of the while loop checks the size. Is the size 0? No, the size is 2. I have 1 and 6. So remove one element. We're going to remove 1. Insert the children of 1. So we're going to insert 0 and 3 into the queue, and print 1 on the screen. Okay, print 1. That's the next element that have to be printed. In the next iteration, 6 is going to be the head, so we're going to remove it. We're going to print it eventually, and the children, which are 5 and 7, will going to be inserted to my queue. In the next iteration, 0 will be removed, 0 will be printed, and it has no children, so nothing else will be inserted to the queue. In the next step, 3 will be removed, as you see, because 3 would be the head after removing 0, and 3 will be printed, but the children of 3, we only has 1 child, so the only child of 3 will be inserted, will be in queue to my queue. So 2 will be the last thing that will be in queued. Then after that, 5 will be removed and will be printed on the screen. Then 7 will be removed and will be printed on the screen. And then finally 2 will be removed and will be printed on the screen. So as you see, the order is basically level by level from top to bottom. First 4, then 1, then 6, then 0, then 3, then 5, then 7, then 2. So that's basically the same order as BFS, and this should work properly. So next thing I want to do is I'm going to run this and make sure that whatever I promised in this video, which means everything should work, is a true promise. That means everything really should really work. Let's find out. So I have called the BFS print here. I have printed the min max values. If it works properly, min and max were 0 and 7. The number of element is 8. The height is going to be 3. It's 3 because, you know, the path from 4 to 2, if you count 4 to 1, 1 to 3, 3 to 2 is equal to 3 hops. So because there are 3 hops from 4 to the deepest child, the height should be 3, and that should be the case. Pre-order should be the same as what I wrote on the screen. Post should be the same. In order should be the same. And then BFS traversal should be the same. Let's try this. I'm just gonna go to the ocelot. I've already done it, but let me clear it one more time and do it one last time here. I'm just gonna first do a GCC to compile everything, and then I'm gonna run it. And as you see, it says 2 is in the tree. Remember, we did a search operation test. So this is correct because 2 is in the tree. 9 is not in the tree. That's correct. In order traversal is 0, 1, 2, 3, 4, 5, 6, 7. That's exactly the same as what I wrote here. Post order traversal is 0, 2, 3, 1, 5, 7, 6, 4. It's exactly the same as what I wrote here. Pre-order traversal is 4, 1, 0, 3, 2, 6, 5, 7. That's correct. Then we have the height, which should be 3. That's correct. The number of elements should be 8. That's correct. The mean value is 0. That's correct. The max value is 7. That's correct. BFS traversal is 4, 1, 6, 0, 3, 5, 7, 2. So that's correct. Everything is working properly, and that's basically all I wanted to say for this video. Thank you.